In geometry, a striking feature of projective planes is the symmetry of the roles played by points and lines in the definitions and theorems, and duality is the formalization of this concept. There are two approaches to the subject of duality, one through language and the other a more functional approach through special mappings. These are completely equivalent, and either treatment has as its starting point the axiomatic version of the geometries under consideration. In the functional approach, there is a map between related geometries that is called a duality. Such a map can be constructed in many ways. The concept of plane duality readily extends to space duality, and beyond that to duality in any finite-dimensional projective geometry. Principle of duality. A projective plane C may be defined axiomatically as an incidence structure, in terms of a set P of points, a set L of lines, and an incidence relation I that determines which points lie on which lines. These sets can be used to define a plane dual structure. Interchange the role of points and lines in C equals to obtain the dual structure C equals, where I is the inverse relation of I. C is also a projective plane, called the dual plane of C. If C and C are isomorphic, then C is called self-dual. The projective planes PG for any field isomorphic to its dual, K, are self-dual. In particular, Disargasian planes of finite order are always self-dual. However, there are non-Disargasian planes which are not self-dual, such as the Hall planes, and some that are, such as the Hughes planes. In a projective plane, a statement involving points, lines and incidence between them that is obtained from another such statement by interchanging the words point and line, and making whatever grammatical adjustments that are necessary, is called the plane dual statement of the first. The plane dual statement of 2 points are on a unique line is 2 lines meet at a unique point. Forming the plane dual of a statement is known as dualizing the statement. If a statement is true in a projective plane C, then the plane dual of that statement must be true in the dual plane C. This follows since dualizing each statement in the proof in C gives a corresponding statement of the proof in C. The principle of plane duality says that dualizing any theorem in a self-dual projective plane C produces another theorem valid in C. The above concepts can be generalized to talk about space duality, where the terms points and planes are interchanged. This leads to the principle of space duality. These principles provide a good reason for preferring to use a symmetric term for the incidence relation. Thus, instead of saying, a point lies on a line, one should say, a point is incident with a line, since dualizing the latter only involves interchanging point and line. The validity of the principle of plane duality follows from the axiomatic definition of a projective plane. The 3 axioms of this definition can be written so that they are self-dual statements, implying that the dual of a projective plane is also a projective plane. The dual of a true statement in a projective plane is therefore a true statement in the dual projective plane, and the implication is that for self-dual planes, the dual of a true statement in that plane is also a true statement in that plane. Dual theorems as the real projective plane, PG, is self-dual. There are a number of pairs of well-known results that are duals of each other. Some of these are Desargues' theorem, converse of Desargues' theorem, Pascal's theorem, Bryantian's theorem, Menelaus' theorem, Siever's theorem. Dual configurations, not only statements, but also systems of points and lines, can be dualized. A set of m points and n lines is called an configuration if c of the n lines pass through each point and d of the m points lie on each line. The dual of an configuration is an configuration. Thus, the dual of a quadrangle, a configuration of 4 points and 6 lines, is a quadrilateral, a configuration of 6 points and 4 lines. The set of all points on a line, called a projective range, has as its dual a pencil of lines, the set of all lines on a point. Duality is a mapping. Plane dualities. A plane duality is a map from a projective plane C equals to its dual plane C equals, which preserves incidence. That is, a plane duality sigma will map points to lines and lines to points in such a way that if a point Q is on a line M, then QIM sigma IQ sigma. A plane duality which is an isomorphism is called a correlation. The existence of a correlation means that the projective plane C is self-dual. The projective plane C in this definition need not be a disargasian plane. However, if it is, that is, C equals PG with K a division ring, then a duality, as defined below for general projective spaces, gives a plane duality on C that satisfies the above definition. In general projective spaces, a duality delta of a projective space is a permutation of the subspaces of PG with Ka field that reverses inclusion. That is, St implies S delta T delta for all subspaces S T of PG. Consequently, a duality interchanges objects of dimension R with objects of dimension n-1-r. That is, in a projective space of dimension n, the points correspond to hyperplanes. The lines joining two points correspond to the intersection of two hyperplanes, and so on. Classification of dualities. The dual V of a finite-dimensional vector space V over a skew field K can be regarded as a vector space of the same dimension over the opposite skew field K. There is thus an inclusion-reversing bijection between the projective spaces PG and PG. If K and K are isomorphic, then there exists a duality on PG. Conversely, if PG admits a duality for n greater than 1, then K and K are isomorphic. Let π be a duality of PG for n greater than 1. If π is composed with the natural isomorphism between PG and PG, the composition θ is an incidence-preserving bijection between PG and PG. By the fundamental theorem of projective geometry, θ is induced by a semi-linear transformation T, VV with associated isomorphism sigma, KK, which can be viewed as an anti-automorphism of K. In the classical literature, π would be called a reciprocity in general, and if sigma equals it would be called a correlation. Some authors suppress the role of the natural isomorphism and call θ a duality. When this is done, a duality may be thought of as a collineation between a pair of specially related projective spaces and called a reciprocity. If this collineation is a projectivity, then it is called a correlation. Let EW equals T denote the linear functional of V associated with the vector W in V. Define the form phi. V times Vk by phi is a non-degenerate sesqui linear form with companion anti-automorphism sigma. Any duality of PG for n greater than 1 is induced by a non-degenerate sesqui linear form on the underlying vector space, and conversely. Homogeneous coordinate formulation. Homogeneous coordinates may be used to give an algebraic description of dualities. To simplify this discussion, we shall assume that K is a field. But everything can be done in the same way when K is a skew field, as long as attention is paid to the fact that multiplication need not be a commutative operation. The points of PG can be taken to be the non-zero vectors in the dimensional vector space over K, where we identify two vectors which differ by a scalar factor. Another way to put it is that the points of n-dimensional projective space are the one-dimensional vector subspaces, which may be visualized as the lines through the origin in knots plus 1. Also, the n-dimensional subspaces of knots plus 1 represent the dimensional hyperplanes of projective n space over K, i.e., PG. A non-zero vector U equals in knots plus 1 also determines a geometric dimensional subspace who, by who equals U0x0 plus unxn equals 0. When a vector U is used to define a hyperplane in this way, it shall be denoted by UH, while if it is designating a point, we will use up. They are referred to as point coordinates or hyperplane coordinates respectively. Some authors distinguish how a vector is to be interpreted by writing hyperplane coordinates as horizontal vectors while point coordinates are written as vertical vectors. Thus, if U is a column vector, we would have up equals U while UH equals UT. In terms of the usual dot product, who equals XP, UHXP equals 0. Since K is a field, the dot product is symmetrical, meaning UHXP equals U0x0 plus U1x1 plus UNXN equals X0 U0 plus X1 U1 plus XN UN equals XH up. A fundamental example: a simple reciprocity can be given by up UH between points and hyperplanes. This extends to a reciprocity between the line generated by 2 points and the intersection of 2 such hyperplanes, and so forth. Specifically, in the projective plane, PG, with Ka field, we have the correlation given by points in homogeneous coordinates lines with equations X plus by plus C Z equals 0. In a projective space, PG, a correlation is given by points in homogeneous coordinates planes with equations X plus by plus C Z plus DW equals 0. This correlation would also map a line determined by 2 points onto the line which is the intersection of the two planes with equations A1X plus B1y plus C1z plus D1w equals 0 and A2x plus B2y plus C2z plus D2w equals 0. The associated sesquilinear form for this correlation is phi equals UHXP equals U0x0 plus U1x1 plus UNXN, where the companion anti-automorphism sigma equals id. This is therefore a bilinear form. This can be written in matrix form as phi equals UHGXP, where G is the times identity matrix, using the convention that UH is a row vector and XP is a column vector. The correlation is given by geometric interpretation in the real projective plane. This correlation in the case of PG can be described geometrically using the model of the real projective plane, which is a unit sphere with antipodes identified, or equivalently, the model of lines and planes through the origin of the vector space R3. Associate to any line through the origin the unique plane through the origin which is perpendicular to the line. When, in the model, these lines are considered to be the points and the planes the lines of the projective plane PG, this association becomes a correlation of the projective plane. The sphere model is obtained by intersecting the lines and planes through the origin with a unit sphere centered at the origin. The lines meet the sphere in antipodal points which must then be identified to obtain a point of the projective plane, and the planes meet the sphere in great circles which are thus the lines of the projective plane. That this association preserves incidence is most easily seen from the lines and planes model. A point incident with a line in the projective plane corresponds to a line through the origin lying in a plane through the origin in the model. Applying the association, the plane becomes a line through the origin perpendicular to the plane it is associated with. This image line is perpendicular to every line of the plane which passes through the origin, in particular the original line. All lines that are perpendicular to the original line at the origin lie in the unique plane which is orthogonal to the original line, that is, the image plane under the association. Thus, the image line lies in the image plane and the association preserves incidence. Matrix form as in the above example, matrices can be used to represent dualities. Let π be a duality of PG for n greater than 1 and let phi be the associated sesquilinear form on the underlying dimensional vector space V. Given a basis, A, of V, we may represent this form by where G is a non-singular times matrix over K and the vectors are written as column vectors. The notation X sigma means that the anti-automorphism sigma is applied to each coordinate of the vector X. Now define the duality in terms of point coordinates by polarity. A duality that is an involution is called a polarity. It is necessary to distinguish between polarities of general projective spaces and those that arise from the slightly more general definition of plane duality. It is also possible to give more precise statements in the case of a finite geometry, so we shall emphasize the results in finite projective planes. Polarities are general projective spaces if Pi is a duality of Pg with K a skew field. Then a common notation is defined by Pi equals S for a subspace S of Pg. Hence, a polarity is a duality for which S equals S for every subspace S of Pg. It is also common to bypass mentioning the dual space and write in terms of the associated sesquilinear form. A sesquilinear form phi is reflexive if phi equals 0 implies phi equals 0. A duality is a polarity if and only if the sesquilinear form defining it is reflexive. Polarities have been classified, a result of Birkhoff and von Neumann that has been reproven several times. Let V be a vector space over the skew field K and phi be a reflexive non-degenerate sesquilinear form on V with companion anti-automorphism sigma. If phi is the sesquilinear form associated with a polarity, then either sigma equals eden phi equals phi for all u x in V, that is, phi is a bilinear form. In this case, the polarity is called orthogonal. If the characteristic of the field K is 2, then to be in this case there must exist a vector Z with phi 0, and the polarity is called a pseudo-polarity. Sigma equals eden phi equals 0 for all u in V. The polarity is called null polarity and can only exist when the projective dimension n is odd. Sigma 2 equals id sigma and phi equals phi sigma for all u x in V. Such a polarity is called a unitary polarity. A point P of Pg is an absolute point with respect to polarity if PIP. Similarly, a hyperplane H is an absolute hyperplane if HIH. Expressed in other terms, a point X is an absolute point of polarity pi with associated sesquilinear form phi if phi equals 0 and if phi is written in terms of matrix G, XTGX sigma equals 0. The set of absolute points of each type of polarity can be described. We again restrict the discussion to the case that K is a field. If K is a field whose characteristic is not 2, the set of absolute points of an orthogonal polarity form a non-singular quadric. If the characteristic is 2, the absolute points of a pseudo-polarity form a hyperplane. All the points of the space Pg are absolute points of a null polarity. The absolute points of a Hermitian polarity form a Hermitian variety, which may be empty if K is infinite. When composed with itself, the correlation phi equals xh produces the identity function, so it is a polarity. The set of absolute points of this polarity would be the points whose homogeneous coordinates satisfy the equation xh(xp) equals x0 x0 plus x1 x1 plus xn equals x02 plus x12 plus xn2 equals 0. Which points are in this point set depends on the field K. If K equals R, then the set is empty, there are no absolute points. On the other hand, if K equals C, the set of absolute points form a non-degenerate quadric. If K is a finite field of odd characteristic, the absolute points also form a quadric. But if the characteristic is even, the absolute points form a hyperplane. Under any duality, the point P is called the pole of the hyperplane P, and this hyperplane is called the polar of the point P. Using this terminology, the absolute points of a polarity are the points that are incident with their polars, and the absolute hyperplanes are the hyperplanes that are incident with their poles. Polarities in finite projective planes. By Wedderburn's theorem, every finite skew field is a field, and an automorphism of order 2 can only exist in a finite field whose order is a square. These facts help to simplify the general situation for finite Disargasian planes. we have, if pi is a polarity of the finite Disargasian projective plane Pg where q equals p for some prime p, then the number of absolute points of pi is q plus 1 if pi is orthogonal, or q 3/2 plus 1 if pi is unitary. In the orthogonal case, the absolute points lie on a conic if p is odd, or form a line if p equals 2. The unitary case can only occur if q is a square. The absolute points and absolute lines form a unital. In the general projective plane case where duality means plane duality, the definitions of polarity, absolute elements, pole and polar remain the same. Let P denote a projective plane of order n. Counting arguments can establish that for a polarity pi of P, the number of non-absolute points incident with a non-absolute line is even. Furthermore, the polarity pi has at least n plus 1 absolute points, and if n is not a square, exactly n plus 1 absolute points. If pi has exactly n plus 1 absolute points, then, if n is odd, the absolute points form an oval whose tangents are the absolute lines, or, if n is even, the absolute points are collinear on a non-absolute line. An upper bound on the number of absolute points in the case that n is a square was given by Sieben. A purely combinatorial argument can establish a polarity pi in a projective plane of square order n equals S2 has at most S3 plus 1 absolute points.